Good evening, everyone. This is Rich Ozer. I'm here with Gerald McKeegan and John Curry, and we're going to try to do some live telescope viewing tonight. And we got some other presentations related to the Perseid meteor shower. There's Gerald waving. Let me get my video going. There I am. I can see myself. Yeah, I jumped in a minute early because someone was complaining that they didn't hear anything. Sorry about that. Now you got a big echo. And there we go. All right. Yeah, we've been fighting all the computer technology tonight, but I think we got it set.
I love computers.
That's the right thing to say.
I did a program.
Gerald got in trouble the other night because he said he didn't like computers, and somebody complained that he was setting a bad example, and we told him he can't say that anymore. All right. Do you want to start by, while we still can, maybe put it on Jupiter so we could...
Okay. All right. Well, we got the telescope set up, so I'm going to go ahead and salute at Jupiter.
Okay.
I guess you're going to be in live mode.
Yeah, I got to share my screen.
All right. All right, here we go. So the telescope we're using is Nellie. Nellie is a 36-inch reflecting telescope. So it uses mirrors instead of lenses. And it is computer controlled. So all I need to do is tell it where I want to look and it will do all the work for me. So looks like we got close, but no cigar, huh?
Oh, you're pretty close. Take a look here. You may want to do a...
Yeah, I can see it on your...
Oh, you got it on your screen? Good.
Yeah.
Great. And I could change the ISO here so it gets a little more detail.
Yeah.
It's a much better night than we've had in recent weeks. And you can see actually a pretty nice view of the cloud bands tonight.
Yeah.
Yeah, true. Gerald can say whatever he wants. I'm trying to adjust the exposure here a little bit.
Yeah.
That's too dark. There we go.
So for those of you living in the Bay Area, you know it's really hot, and that's because we've got a high pressure area sitting on top of us. We do have some high altitude cloudiness, remnants of a hurricane that was in the Central Pacific that is starting to blow some clouds up here. In fact, we have a forecast later on tonight for possible thunderstorms. But right now we've got this high pressure area sitting on top of us. That makes the air very steady. It also makes it very hot. And steady air is what astronomers like because it makes the viewing a lot better, what we call the seeing a lot better. So you notice that Jupiter looks pretty steady. It's not going in and out of focus. And that's what we like.
Yeah, I mean, last week it was like looking at it underwater.
Right,
Under
running
like,
water.
Yeah, no, it's like, when I used to jump into a swimming pool and try opening my eyes and see across the pool. That's what Jupiter looked like last week.
But we do have another problem, though. We do have the high cloudiness that's slowly blowing in. So the clouds may periodically pass in front of Jupiter, and you may see it dimming and brightening. But that's because of the clouds. It's not a telescope defect or anything like that. So you can see the two dark bands. Jupiter is a gas giant. It's 88,000 miles in diameter. It's 11.2 times the diameter of the Earth. So it's a huge planet. And it is a gas giant. So it's mostly a lot of dense gas. But the planet rotates very rapidly. A day on Jupiter is only 9 hours and 50 minutes long. So you've got this big giant planet that's rotating very rapidly. And it does get high and low pressure areas in the atmosphere and on Jupiter, just like we get on Earth. But because of its rapid rotation, it wraps those highs and lows all the way around the planet. So those dark bands that you see are actually the result of low pressure areas in the atmosphere. And the light bands tend to be the higher pressure areas in the atmosphere. If you were to get close up, you'd actually notice a difference in the actual height of the clouds in those two regions. Now, I don't think we have a red spot tonight.
We don't.
Yeah.
Not tonight.
Yeah.
Yeah. So sometimes, sometimes we'll imagine that we're seeing the red spot, and it's really not true. The red spot, though, when it does come around, is it's pretty dramatic, and I think we've got both of our audio.
So, Rich, if you could reset your exposure to overexposed Jupiter, we might be able to see some of its moons.
Yeah, let's give that a shot. All right, I'm going to try going up to ISO 1600. There we go.
Still don't see any moons.
You should see that. Let's brighten it up some more. I'm seeing it on the source laptop. Let's go a little brighter then.
Oh, way off to the side there.
Now there's
there's one to the left.
I'm going to keep bumping it up here until it's more obvious through Zoom. Zoom is kind of filtering it out.
Oh, there you go. There you go. There we go. Yeah. All right. So we see one to the left, one to the right, close in, and then one way out on the right.
Yeah.
So
Europa already close, and Ganymede's way out to the right.
Okay, so John is looking it up. Io and Europa are the two that are close in, and then Ganymede is the one way off to the right. And I guess Callisto,
They're out to the right.
Callisto is out of the frame. Yeah, yeah. So these four bright moons are what we call the Galilean moons. They were discovered by Galileo in 1610. And he at first wasn't quite sure what he was seeing. Galileo, when he first pointed his telescope at Jupiter, he was a good scientist, so he sketched what he saw, and he sketched the planet itself, which looked like a little round ball to him, and he noticed what he thought were stars on either side of it. So he sketched the stars. He then looked again the next night, and darn if those stars hadn't changed position. And so he did this over several nights, and he realized what he was seeing was moons orbiting around Jupiter, which was quite a surprise, but it confirmed what we call the Copernican theory that says not everything orbits around the Earth. That planets can have their own moons, and they orbit around the planets.
It's one of the most controversial examples of observing small dots. And it created a real storm of problems for Galileo.
Yeah, who ended up being under house arrest because he advocated that theory. So the four Galilean moons, they're the biggest moons of Jupiter: Io, Europa, Ganymede, and Callisto. But Jupiter has many more smaller moons. In fact, I think we're up to 84. Is that right, John?
It's 84.
84 moons around Jupiter. Jupiter has extremely strong gravitational pull. So any bodies that get close to it can be captured by its gravity and end up being in orbit around it. And in fact, some of the material that formed the planet originally likely also formed some of those moons as well. So it's got a lot of moons, but most of those moons are very small, only a few kilometers across, or maybe a few dozen kilometers across. So they're too small for us to see with this telescope. In fact, for any telescope here on Earth, they're very hard to see. Many of the moons that we know of today were actually discovered by spacecraft orbiting around Jupiter or by the Hubble telescope.
There's a good question from Germ, and he wanted to know, why does the red spot storm always persist? Is it a permanent high-low pressure system, I have certain ideas about that. Why don't you go ahead and
Well, it's basically a hurricane on Jupiter. Why it has lasted so long, we are not really sure. We're not sure why it has lasted as long as it has. But for as long as people have been taking pictures of Jupiter, the red spot has been there. Although it does not remain the same, it has faded somewhat over the last several years. In fact, I kind of joked that it's no longer the red spot, it's now kind of the brownish spot.
yeah, but it's reddened up again in the last year or so.
Yeah, so it's changing all the time. And why it persists is not well understood.
I think when you're dealing with gas giants the size of Jupiter, that things that appear to be weather systems are not the same as weather systems here on Earth. That you're really dealing with massive fluid dynamics phenomenon.
Right.
And they have strengths and persistence that kind of go outside the meteorology, science or meteorological science that we use to study hurricanes and storms here on Earth. So I think it's something different. It's something much deeper and certainly more powerful. The question is will it always be there? Do all gas giants have large storms? Well, there's evidence that in fact they do. There is a white storm on Neptune that looks very similar to the Great Red Spot in shape and character, and it persists much like the red spot does. And Saturn also has phenomenon that are visible to our telescopes, like the hexagon storms at the top of the planet. There's basically cloud patterns that look like hexagons. And there's all kinds of interesting things that happen with the large amounts of material that are in gas giants. And I think we just really barely understand it.
Right. Although trying to understand them actually helps us understand the weather on Earth, because the processes on Earth are not as dynamic as they are in Jupiter, but the physics is the same. So by studying weather phenomena on Jupiter and Saturn, we can actually understand weather on the Earth a little bit better.
Great.
All right.
Well, these were nice views of Jupiter tonight. If we want, Saturn is clear too. It's just a quick.
Yeah. Okay. The clouds have parted.
Yeah.
Okay.
Let's
So
turn the exposure down a little bit so we get a better view.
all right. Tell me when you're ready, and
I'm
I'll
ready.
Slew to Saturn.
I am ready.
Now, right now, Saturn and Jupiter are pretty far apart. If you were to be looking up at the sky right now, Jupiter is a bright object, sort of in the south eastern part of the sky, southeast. And then to the left of it is Saturn, which is not as bright, although it is one of the brighter objects up there. But if you hold your hand at arm's length and put 3 fingers up, the spacing between the 2 planets right now is about the spacing of your 3 fingers held at arm's length. But over time, because Jupiter is orbiting the Earth faster than Saturn, Jupiter is catching up. From our point of view, Jupiter is catching up with Saturn. And in December, they will be so close together in late December that we'll be able to see both of them in the same telescope view. So keep your fingers crossed that the weather cooperates in December, and we might actually be able to see both planets in the same telescope view.
I might point out that they're not close together physically, just angle-wise.
Right. Yeah, John just pointed out it's strictly our viewing angle that makes them look close together. Physically, they are not close together. They're actually quite far apart, nearly 5 million or 500 million miles apart when they're closest to each other. So you can see Saturn, you see the rings, You might be able to make out a little bit of banding on Saturn's clouds.
I am seeing every once in a while the Cassini division pop in and out right where I'm putting this weird looking cursor. You have to really watch carefully, and I'm just see every once in a while a little black band. And what that is it's a separation in the rings caused by one of Saturn's moons that basically clears a path in all of the dust and ice that forms the ring. I think that's Pan, right? Is that the,
Pan is one of Pan does the Enki division.
oh,
not
Pan
the
does the
Cassini.
Enki one. Cassini is a different one. Do you remember which moon does Cassini? Which one causes?
Actually, Cassini is caused by Mimas, which actually orbits outside of the ring system. But there is a mean motion resonance at the Cassini division with Mimas. So a mean motion
really
resonance, if you have two objects orbiting a planet, and it happens to be that the orbital period of one is a whole number multiple of the orbital period of the other. So one, for example, orbits and takes twice as long as the other. We say that's a mean motion resonance, because what will happen is that as one laps the other, it always laps it at the same point relative to the parent planet. So that's called a mean motion resonance. And when you get mean motion resonances, it's very hard for objects at the resonant point to stay put. So what's happening is there's a moon called Mimas, and the mean motion resonance point for Mimas is at about the distance of the Cassini division. So ice particles that get into that part of the ring system want to get kind of shoved back out into other parts of the ring system, which keeps the Cassini division nice and open.
That's very interesting. Thanks.
Yeah.
We had a question. Are Jupiter's and Saturn's core hotter than Earth's core? I mean, honestly, we don't know. We've never sent a probe that far into Jupiter or Saturn. It would take a lot of doing to do so. We don't even really know with any certainty what the temperature of the Earth's core is, right?
Right,
And,
right.
But there's reason to believe that the center of these gas giants have accumulated rocky material that has become molten, and it might be, as hot or hotter than what's at the center of the Earth, simply because there's so much more gravitational force involved, so much more pressure.
Right, right. So the internal heat of a planet can be caused either by compression because of its strong gravitational field, and or radioactive decay. Much of the heat in Earth's core is actually the result of radioactive decay. There are radioactive materials down deep in the mantle and the core, and as they decay, they generate heat. And that is what drives much of the heat of the interior of the Earth. So the extent to which that there are decaying radioactive materials in Jupiter's core or Saturn's core, that could contribute to the heat. But you also have a lot of mass, which provides a lot of compression, which also generates heat.
I was asked here about the red dot that's right here. Boy, I wish I had a way to paint over that. That is actually a hot pixel on the sensor of the camera, and isn't a real thing at all, other than an artifact of the camera. It's an unfortunately positioned hot pixel. So
yeah, we have a couple of things that happen to cameras, and hot pixels are one of them. Those are pixels that, for whatever reason, they don't turn themselves off even when they're looking at a black background. There's another thing that causes occasional hot pixels, and that's cosmic ray strikes, which you won't see in an image like this. But in a little while, we're going to show you some images, and you're actually going to see evidence of cosmic ray strikes. So,
all right, yeah, but it does look like a red dwarf star.
yeah.
I mean, it's a great guess. Yeah,
Submit
wish.
your data to the IAU. Maybe
Yeah,
you'll
yeah,
be
yeah.
the-
Maybe they'll name it. They'll name that hot pixel after me. All right. What do you think? The reason I have to keep making it brighter and dimmer and all that is we're watching clouds march in front of the planet on and off. Do you want to take a break from the viewing and talk about the asteroids?
All right, all right. I
presentation?
thought we were going to do Alberio.
Oh yeah, let's. You want to do that
Yeah, let's.
now, or do you want to do that after the
Yeah, might as well do it now.
Okay.
I got to find it.
Right, we're gonna go to Alberio because that's a bright target. Alberio is a kind of a dramatic double star system that's known for its distinct colors. The
Okay.
two stars are quite different from one another. So you
I'm going to go up to Altair and use it to
Okay.
sync.
Sure. Yeah, we should be able to get it. There's Altair. Okay. Yeah, we should be able to get through it.
Okay, so let's sync on that.
That's not Alberio.
Yeah, that's the star Altair, one of the 3 stars in the summer triangle. Altair is 17 light years away. So okay, here we go.
A shot.
Red dot question was about
There we go. Oh, that's good. All right.
All right, let me center that up a little bit.
I'm going to increase the exposure time a little bit. Okay.
Okay,
So
so
you can see that they're very distinct from one another. One is a blue star and one is a red star, and or kind of an orange star. Yeah. And these are the UC Berkeley colors.
yeah,
Somebody asked once, "Is there a Stanford double star?" And I said yes, there is. It's in Cassiopeia. Eta Cassiopeia is the Stanford color.
the question is which one gets the axe?
Yeah, that's right. So the color of stars is very revealing in astronomy because it really. Whoops, did we lose it? Oh, it was the clouds.
It's clouds.
So they're twinkling. The color of the star tells us a lot about the temperature of the star. And just like a blue flame is hotter than a red flame, as kind of a rough analogy, a blue star is a much hotter star than a red star.
When you can see it.
Yeah, when you can see it, that's right.
Yeah.
So I'm actually going to up the exposure a little bit more.
Okay.
If we can.
Yeah, what Richard said is a good example. If you could imagine a candle flame, if you look at the part of the flame close to the wick, it'll be bluish in color, and that's the hottest part of the flame. But as you come up away from the wick, get higher up in the flame, it goes from yellow to orange and then red, and then it is no longer visible. And as you get farther away from the wick, it gets cooler. So blue is hot, yellow is moderately cool, and orange or red is very cool. Now these 2 stars, the dimmer one is the blue star, and the brighter one is the orange star. There's a lot of debate about whether they are actually gravitationally bound to each other, and there continues to be debate, even though we know they are actually a few light years apart. But it's possible that because of the strong gravitational attraction between them, they are in fact orbiting each other.
Well, the last study of that was of any real significance was done by the Hipparcos mission, which was a satellite or observatory sent into space to actually study the orbits of double stars, among other things. And the study of Alberio it led to, a lot of researchers to conclude that they are in orbit around one another. But it's still uncertain. There could be that one is moving towards us, the other is moving away from us, and they may in fact not be in a real orbit around one another. They may just be influencing one another on their own independent paths.
Now, one of the things about it, you see one that's brighter, the yellow one is brighter than the blue one, and that may lead you to believe that it's closer, but in fact, it's the farther away of the two stars. The yellow one is a star that's approaching the end of its life, and as stars get close to the end of their lives, they swell up, become giant stars, and that causes the surface of the star to cool. But because they're larger, they have more surface area to radiate light. So even though it is brighter, it's actually farther away. It just appears brighter because it has more surface area radiating light. It's cooler, it's farther away, but its bigger size makes it look brighter.
We had a couple more questions. One had to do with whether there are planets around these stars in Albireo. We don't know. We've not detected any. There's been no observation of planets. Detecting planets around distant stars is not a trivial thing, and it involves many observations of the star, see if there is any dimming, or to see if we can detect a wobble in that star as the planets orbit around it. And both require very sensitive instruments, and the stars can't be too far away. That makes it kind of hard to tease the data apart if the star is too distant. So it's a complete unknown on whether these stars have any planets. You could take a wild guess and say probably. I mean, it seems like most of the stars we study, where it is close enough and we are able to get data, we do find some planets around them. With double stars, there's if they're in orbit around one another, there's a greater chance that their planets are tossed out into space because of the gravitational forces. But all the same, it's probably a good bet to say yes, but we really don't know.
Right.
What was the other question, John? There was somebody who had... Oh, Venus. Yeah, we're not going to be seeing Venus tonight because it's not out until tomorrow morning.
Yeah. Now, Mars is going to be up later on tonight. Mars rises about 11 o'clock or so, but it will be very low in the eastern sky until, around midnight or later. So if you're up that late, look off to the east, you'll see a bright orange star, and that's actually the planet Mars. And over the next several months, Mars will be higher and higher in the sky each night at the same time. Eventually, it will be high enough for us to observe it, say at 9:30 or 10 o'clock at night. So a future virtual telescope program will include Mars. So stay tuned.
So there was a question about the position, location of these. So, when we're looking at other stars, we're usually looking at stars that are in our own galaxy, right? In the Milky Way galaxy.
Right.
So the question was, are these stars, in our system? And well, they're not in our solar system. And our solar system consists of the sun and the planets with which we're familiar. But all of the stars we see in the sky, including this double star system, are part of the Milky Way galaxy. And of course, we see other galaxies in the sky as well. Those are much more distant than the individual stars that we see. And they, of course, are composed of their own stars, but much farther away than the ones we see on a typical night. So I hope that answers the question.
And with this telescope, you won't be able to pick out individual stars in other galaxies. You just see the combined
unless they go
glow.
supernova.
Yeah.
And then we can pick them out.
Yes. Can we find a few of those?
Yeah, those are always fun.
Yeah. So
The one question is, how do we estimate the distance between the Earth and the stars? Well, there's several methods. Do you want to answer that, or do you want to?
Sure,
Yeah, why don't you
sure.
go for that one?
Yeah, there's a couple of different techniques that we use. The one that works best is to use the parallax method. If you imagine how you judge distance with your eyes, you have two eyes, you look at an object that's, say, 10 feet away. Your two eyes don't point in exactly the same direction. They point slightly inward, and the angle between them is what you use to judge the distance. That's a very common technique. It's called parallax. You can demonstrate it pretty easily if you hold your finger out in front of you and close one eye and look at where your finger is relative to the background, and then shift to the other eye. You'll notice that your finger appears to shift position, and that's called parallax.
And we're all sitting here now with our fingers in front of our computers.
Yes.
Going.
Make sure you hold.
We want to make sure he's right.
This finger. Make sure you're holding the right finger.
Yeah. Make sure. Yeah, we better use the right finger. That's
Okay.
right.
So anyway, what we do with stars, we observe a star at a certain time of the year and where it is relative to the background stars, stars that are much farther away. And then we observe it again 6 months later. During that 6-month period, the Earth has orbited halfway around the sun. So the Earth is about 93 million miles away from the sun. So in 6 months, we've gone from one position to another position that's 186 million miles away. So you've got this huge shift in your observing position. And that results in a shift in the position of nearby stars compared to much farther away stars. And using that technique and with some pretty simple trigonometry, trigonometry is simple for some of us, maybe not for others, but anyway, using simple trigonometry, you can calculate the distance. Now, this works well for stars that are less than 100 light years away, but you get farther than that and it becomes more difficult. There are some techniques that can extend that a little bit more. For example, using satellites like the Gaia satellite that's up right now. But basically, it only works for things that are relatively close. But within that sphere, let's say 100 light year sphere, you've got all kinds of stars. And we see stars at various stages of their lives. We see stars that are different masses. We see star clusters and so on. And from that, we develop quite a catalog of star types and what their characteristics are like. And we begin to associate the characteristics of the star with the brightness of a star. We then look at stars that are much farther away, stars that are 300 or 500 light years away. And we study the characteristics. We analyze use spectroscopy to analyze their characteristics. We look at their color, the distribution of how much light comes at different wavelengths of color and so on. And we characterize those more distant stars. And then we compare them to what we learned about the close-in stars. And from that, we can gauge, all right, a certain star with these characteristics should be this bright. And we measure how bright the star is actually. And then using what's called the inverse square law, we calculate the distance. The inverse square law says that the brightness of an object is proportional to the inverse of the square of the distance. So for example, if a star is twice as far away, it will be 1/4 as bright. If it's 10 times farther away, it'll be 1/100th as bright. So using the inverse square law and our understanding of star characteristics and how they translate to star brightness, we can calculate the distance. It's not as precise as the parallax method, but it works pretty well.
Great, thank you.
All right.
Very complete answer. Thank you, John, for answering Carol's question. Yeah, I was going to mention that, a couple of people had asked, what are we looking at? Because they tuned in late. So we're looking at a double star probably a double star system. They're in orbit around one another.
Plus a red hot spec.
Or they're two individual stars that are reasonably close, and we're wondering whether they're double star. One red, one orange, one blue. It's called alberio. The two together are called alberio. If you were to look in the constellation Cygnus in the right location, it would appear to the naked eye as a single star, and it was named alberio. With a pair of binoculars or a telescope, you're able to see that it's actually two components. And they don't have individual names that are anything other than an SAO number. If you were to look them up, they would have a numerical, each have a numerical name. But the system together is called, it's either a system or an asterism, is called alberio.
Yeah, for the latecomers, the red dot you see, which doesn't vary in brightness, is
I'm
actually,
gonna hide it with my cursor.
yeah, there you go. It's actually a camera defect. So ignore that.
Yeah, ignore the red dot. Time for a different camera. Now that red dot it gets worse as the sensor heats up. That red dot has been there since day one on this camera.
Yeah.
And I always process it out of my images if I'm taking astronomical images. But in this case, there's nothing I can do about it. All right.
All right. Well, shall we talk about an asteroid?
Yeah, why don't you do that? And that way I can let my camera cool off a little bit.
All right. That's a good idea. All right. I'm going to share my screen here, hopefully.
I have to unshare first.
Okay.
So I will stop sharing. And now
All right,
you should be
now
able
I
to
can, now I can
share.
do it. There we go. Okay, where are we? Here we are. Oh, let's first do the meteor shower.
Right.
All right. So a lot of you probably are aware that we had a meteor shower earlier this week, the night of the 11th and the morning of the 12th. And although this was not as active as it normally is, this is called the Perseid meteor shower. There were quite a few of them out there. And a couple of our Chabot astronomers were able to capture some images. So the one you see here, this was taken by David Shaw, who's one of our telescope operators at Chabot. David has a cabin up near Lake Almanor, so he gets some pretty dark skies. So you can see one of the meteors, and you can also see the central hub of the Milky Way. So I don't know if you can see my cursor or not.
Yeah.
This is the central hub of the Milky Way. So you can tell that he was looking south. This glow is sky glow from all those inefficient city lights, probably somewhere around Sacramento or something like that. And this is the Milky Way right here. And this is the central bulge of the Milky Way. All this dark stuff is gas and dust out in space. And this is one of the meteors. So he got one, and then hopefully I'm going to be able to switch here to the other. Maybe not.
I see it.
Oh, here
David,
we go.
that's a good shot, by the way.
Yeah.
I really like that
All
photo.
right. Okay. This was taken by Rick Taft. He went up to Isleton, which is up on the Delta, and took these images. And what he did is he just opened the camera up and left it open for a while. And he did this multiple times. And he was able to capture quite a few of the meteors, not only the Perseid meteors, but the occasional, what we call sporadic meteor. Sporadic meteors are just the normal, every once in a while type shooting star, whereas the Perseids all should be sort of emanating from the same point. So if you look, you'll notice that a lot of these streaks kind of go back toward this part of the sky. So this streak comes back towards that part. This one kind of comes back towards that part. This one all comes back. That's called the radiant. And the radiant for the Perseid meteor shower is the constellation Perseus. So what Rick did is he ended up with multiple pictures, and then he combined them to produce this image, which shows a lot of meteors. So pretty cool shot.
Yeah, I think it's great. He picked the right time here too,
Yeah,
because
this glow is actually the moon right here. The moon came up
so
shortly after midnight.
yeah, so he was taking this around 12:30 at night.
Yeah,
It looks
yeah.
like. Yeah, I was looking for them in Concord. I was over in a darker area of Concord, and I was seeing one every 20 seconds or 30 seconds or so.
Well, you did better than I did. I was at home in my backyard. I saw one meteor at 2:25 in the morning.
Oh man, yeah.
So, but I'm in the middle of Walnut Creek, and I got a lot of sky glow.
Oh, so
So I'm going to stop this for a second. I'm going to switch to a different thing that I want to share with you.
yeah. Well, we could talk about this. So, yeah, if somebody was asking, how do we predict meteor showers? Well, the reason meteor showers happen is because the Earth's orbit passes through the remnants of comets that have intersected that orbit at some point in the distant past. So if you imagine, imagine this photograph you're looking at. Actually, if you could share Rick's photograph again.
Let's see here.
You had it there for a sec. It was there and then
There
it
you
went
go.
away. Okay. So assuming, let's just pretend that this is the radiant. What's interesting about the radiant is you think of the Earth's atmosphere kind of as a windshield in your car for the purpose of this discussion. So we're traveling through space kind of in the direction of the radiant, right? And you're hitting a whole bunch of bugs, right? And those bugs are splattering against the windshield. In this case, they're little rocks, and they're hitting the atmosphere and they're burning up in the atmosphere. And the reason those clumps of rocks are there, those collection of rocks are there, is because once upon a time, a comet passed right through that part of space and left a bunch of debris. And now we're traveling through space at a very high speed in orbit around the sun, and we're hitting that spot. And the density of the rocks for that particular pass of the Earth through that field of debris, the density of the rocks is going to determine how interesting that meteor shower is. So that's why, 1 year the Perseids are, a memorable meteor shower, and the next year no one remembers even seeing a single meteor, right? The Leonids in particular are like that. The Leonids are in November, right?
Right. Yeah, around November 18th.
There are times where I have seen Leonid meteor showers where it looks like somebody has turned a shower on, and in the shower, right?
Yeah.
You're looking at the shower head, and it's just this constant stream of debris hitting the Earth's atmosphere, and countless numbers. I mean, hundreds and hundreds and hundreds in just a very short period of time. And then the next year you'll think, oh, I want to see that again, and you won't see anything, right? Because that for that particular pass in the orbit, the debris has moved on, and we're waiting for another clump sometime in the future to hit that spot. And that's a long answer to the question, which is, do we predict them? Yes, because we're always passing through that same trail of debris at the same time every year. So the Perseids are always at the same time every year. The Leonids are at the same time every year.
Yeah, these are particles, little rocky particles. Some of them no bigger than a grain of sand. A few of them are, the size of a pebble. Once in a while you get one fist size, but most of them are pretty small. They're left behind by the comet Swift-Tuttle, which orbits around the sun every 133 years. And each time the comet gets close to the sun, the ices on the comet sublimate. All these particles are embedded in the ice. So as the ice sublimates, which means it goes directly from solid to gas, releases all those particles, and they get dropped into that orbit, and they stay in orbit around the sun. And we pass through that stream of particles every year around August 12th. All right.
I think that's it on meteor showers.
Okay. Well, I got something else to share with you. Speaking of things flying around out in space, we had a new near-Earth asteroid get discovered a couple nights ago. So let me see if I can get this up and going here. Here we go.
I'm seeing your presentation. Oh, yeah, here we go. That's
All right. So a newly discovered near-Earth asteroid is called 2020 PL2. That's the sort of unofficial designation. The official coded designation is K20P02L. But this is a newly discovered asteroid. It was discovered early Thursday morning, August 12th. Actually, probably in the middle of the meteor shower, it was discovered by the Atlas survey telescope, which is on Haleakala in Hawaii. And that's a survey telescope. It's a telescope that just surveys the entire sky. It's actually a whole bunch of telescopes clustered together that move together as they survey the sky. This asteroid, we think, is somewhere between 66 to 150 meters across. Because of its distance and size in our images, we can't really tell you exactly, but judging by the brightness, we think it's somewhere between 66 and 150 meters across. For those of you who don't speak metric, that translates to about 218 to 495 feet. So it's a big asteroid. Now, the picture you see is not this asteroid. It's just a asteroid image that I happened to grab. It's another asteroid that we had a spacecraft fly by. But I just threw that in there to, keep you entertained. That's not the asteroid. You'll see the asteroid in a minute here. So this asteroid has an orbital period of just under 1 year. It's about 360 days. And we call it an Aten class near-Earth asteroid. We give different names to different classes of near-Earth asteroids. An asteroid that spends most of its time, or a lot of its time, closer to the sun than the Earth, but crosses the Earth's orbit. That's called an Aten asteroid. This asteroid, when it's closest to the sun, it's actually closer than the planet Venus is to the sun. It's only about half an astronomical unit, so it's about half the distance between the Earth and the sun. When it's farthest, it's almost as far as the planet Mars. So it's in a highly elliptical orbit. But fortunately, that orbit is highly tilted compared to the Earth's orbit. It has an inclination of 34.6 degrees. So its orbit is angled. So even though it crosses the Earth's orbit, it doesn't cross right through the Earth's orbit. It crosses either above or below the Earth's orbit. So the closest it actually ever comes to the Earth's orbit is about 1.3 million miles. So although we call it a near-Earth asteroid, it's not that near an Earth asteroid, but it's a pretty good size one, which makes it relatively easy to see in our telescopes. So this time around, when I was observing it last night, it was at a distance of 4.4 million miles, which is, it actually got a little bit closer than that when it was at its closest approach to the Earth, but not quite to 1.3 million miles. So this was, again, discovered on August 12th. I did some observations last night. While I was observing it, it had a magnitude of 17.2 in the red part of the spectrum. Now, astronomers use a magnitude system to measure basically the brightness of a star. And the bigger the number, the dimmer the star is. The difference between each unit in the magnitude system is 2.512 times. So a star that's say magnitude 3 is 2.512 times dimmer than a star that's magnitude 2. So the dimmest star that you can see with your naked eye is a little dimmer than magnitude 6. This asteroid, when I was observing it the other night or last night, was at magnitude 17.2, which makes it 25,130 times fainter than the faintest star you can see with your naked eye. So it's pretty dim, but fortunately with Nellie, we got this great big mirror. It gathers a lot of light and it makes it pretty easy to see. So here's the first image that I took last night. And you can see a bunch of stars in the image, and something I want to explain about this image. If you're used to seeing nice, pretty astronomical astrophotography images, you're probably thinking, what happened here? Actually, those pretty astronomical images are highly processed. There's a lot of work done to make the stars look like nice, sharp pinpoints of light and make the background look black. But when we're doing science, we don't want that. We want to see every photon that we have gathered by our telescope. To do that, we do something called stretching. So we take the brightest object that we see, the brightest star that we see in one of these images, and we stretch the image so that is the brightest pixel in the image. So the pixels that for this camera that we're using has 65,000 levels of brightness. The brightest pixel in the image was only about 1,000 brightness levels. So to stretch it, we stretch that image, that one pixel, till it's the full 65,000. And that causes all the other pixels to be stretched as well. So as a result, very faint objects appear, but it makes the background look all mottled and gray.
Think of it as like amplifying.
Right.
It's an amplification process. And it's as if you were going to amplify sound in a room, right? If you turn up the microphone to the highest possible level, then you start hearing the whispering in the back of the room, and you also hear kind of a buzzing noise. So you could think of all of this kind of gray field that Gerald's talking about, the modeling, and some of the visual noise there is the equivalent of that buzzing noise if you had an amplifier with sound.
Right. So this was the first image I took. This was a 3.5 second exposure. And the asteroid is in this image, but it's very, very faint. The reason I only took a 3.5 second exposure is because the asteroid was moving pretty rapidly. It's still close to the Earth, so its motion through the sky is fairly rapid. And if I were to take a long exposure, it would make the background look darker and all the stars look sharper. But the asteroid, instead of being a point of light, would be a streak, and it would be a very faint streak, and it'd be even harder for us to pick it out. So I took a whole bunch of 3.5 second images, hoping to capture the asteroid and its motion just with those 3.5 second images. And I had some luck, and I'll give you an idea what it was like. So what we do is we take a bunch of images, and then we blink through them, kind of like make a little mini movie. So I'll show you what that looks like. Here you go. All right. Now the asteroid is in there, and if you look around, you might be able to pick that out. It's very faint. I'm kind of used to doing this, so my eye picks it up pretty quickly, but most people look at this and say, I don't see an asteroid. You may notice some bright flashing though. So there's a bright flash right here. That's a hot pixel. That's what Richard was talking about a while ago. There's another one down here. Those are hot pixels. They're caused by cosmic ray strikes. So cosmic ray hits a pixel, causes it to momentarily light up. And so we see those bright flashes, but those aren't the asteroid.
I don't see it.
Well, I'm gonna give you a hand here.
I'm staring at this thing and I don't see it.
Look right there.
Oh yeah, okay.
Can you see the little dot?
Yeah, that oval is handy.
Yeah, see, that's how we find asteroids. We look for
We
the
look for the oval.
oval in the sky. Right. So just taking one of the individual frames again, here's an individual frame. This is the one where the asteroid was brightest. There was a little bit of cloudiness last night, so it was going in and out. Also, this is taken over time. This is over about a 15-minute period. And the asteroid is slowly rotating during that time. So we sometimes see a brighter face and sometimes see a dimmer face. So this is the image where it was brightest of those 6 images. And there you see it right there. But this is, although we can see it, it's too faint for us to get data. We want what we call a high signal to noise ratio when we get data. Signal to noise ratio is the ratio between how bright the asteroid appears and how bright the background blotchiness is. And we want the asteroid to appear to be at least 5 times brighter than the background. It doesn't quite make it in this image, and the rest of the images, it's even less. So we use another technique, and it's a stacking technique. If you've been with us over the last several weeks, we've talked about stacking images to make things look brighter. But with an asteroid, because it's moving, we have to use a different technique. Because we know the direction and approximate rate at which the asteroid is moving through the field of view, we stack based on the motion of the asteroid. So what we do is each time we stack an image, we offset the image based on the expected motion of the asteroid. And when you do that, when you have the stack put together, all the stars have shifted, but the asteroid ends up being in the same place in the frame.
It must dump a lot of the noise just from doing that, right?
Well, we're using not an averaging technique.
Oh.
We're using an additive technique.
Oh, I see.
Okay. So this is what it looks like. All right. So this is a stack of 5 individual images, individual 3.5-second images. So we've got 17.5 seconds, I guess, is what the total image time. But now you can see that the asteroid is much brighter. It's a single spot because we've stacked each image so that the asteroid is in the same spot in the stack, but that makes all the stars shift in each image. And you can actually count the individual star images here and see that I've stacked 5 separate images to produce this combined image, which makes it much brighter. We get much better signal to noise ratio. And because before we did this, we did what's called plate solving of these images, which allows us to translate pixel position to the coordinate system we use in astronomy. We're actually now able to pick that star and get the data, its position during the midpoint of these 5 images. So we know when the first image started and we know when the last image ended, and we pick the midpoint, and that's the point at which we see the asteroid here. So just to kind of further show this, this is all these stacked images put together to form a little movie. Now, again, it was cloudy that night, so you can actually see some of the thin cloudiness waving by the image as you watch this. But now you can see the asteroid much better. You can also tell that the asteroid is slowly rotating, so it changes brightness over time. We also see those hot pixels again. There's one right there, and then there's another one down here. They are part of the image stack, so they're still there. And this is how we find some of the really faint asteroids. So I thought it'd be kind of interesting just to share this with you. Our telescope here, Nellie, is part of a global network of observatories that searches for and tracks near-Earth asteroids. And we do this process pretty often. And we get data from these images, and we submit that data to the Minor Planet Center. we figure out what the exact coordinates of the asteroid is in each of the individual images, also how bright the asteroid is, and the exact time of the image. We submit all that to the International Astronomical Union's Minor Planet Center. They will combine our data with data from other observatories and calculate the orbit of the asteroid and catalog it and use that data to figure out whether or not the asteroid poses a threat to the Earth.
Gerald,
Yeah.
someone wants to know what was the time interval between your shots?
The images, what I did is I just set the camera to take 30 individual frames at about roughly 15-second intervals. So the total time from start to ending was about 7.5 minutes or so. And like I say, this
And
was
you, and it
because
looks like, and it looks like you grouped 5 or 6 together for each stack.
each
and
stack is
animated the results of that.
right.
I see.
Yeah. So each stack is a stack of 5 individual images, and so there are 6. Because I had 30 images, there are a total of 6 individual positions that you see here. So this is how we do it.
David sends his compliments.
My daughter, or my wife rather, teases me all the time that I spend a whole lot of time up at Chabot watching little dots fly by.
Yes,
So,
you do.
On a computer.
on a computer, yeah, which I hate.
Yeah,
I can't say that. Can't
I
say
can't say that. Stop
All
that.
right. All right.
All right. How are we doing time-wise? It's 10:30.
Yeah.
We do have some time if you want.
Yeah, we still got quite a bit of cloudiness.
Yeah. The best we could do is put it back on Jupiter if you want, but
Yeah, we can do that.
yeah, but it doesn't.
I know,
Telescope will get through that. Yeah, sorry. I mean, we're limited on what we could see tonight because the clouds are actually thickening up.
Yeah. There's a forecast for thunderstorms later on tonight. So, all right, I'm going to slew to
Time to set up the
Altair.
camera and wait for lightning strikes.
Yeah, there you go. I'm going to slew back to Altair. We'll use it to
Yeah, right.
synchronize. If you can switch so we can see your screen.
Yes,
Rich.
I will do that. Stand by.
What's the humidity?
I slew to Altair to synchronize the telescope.
All right, let me get it into. There we go. There's Altair.
Okay, so we need to.
Now you notice that now that the camera has cooled down, that red dot is a lot dimmer. But it will brighten up as the sensor gets hot again.
All right, so we're synchronized. And let's go to Jupiter. Here we go.
Okay.
All right.
I'm gonna fix the exposure here a bit. There we go.
Okay.
That's not bad.
Yep. Once again, we can see the banding on the planet. Now, Jupiter was at what we call opposition back in mid-July, I think it was. Opposition is when Jupiter, Earth, and the Sun are all lined up in one line. So at local midnight, Jupiter would be exactly on what we call the meridian, which is an imaginary line from the South Pole through the zenith to the North Pole. Jupiter would be on that line at local midnight, which is not the same as our clock midnight. Our clocks, we're working on daylight saving time, or as some astronomers call it, darkness wasting time,
Yeah.
or darkness squandering time. Yeah, yeah. Astronomers hate daylight saving time. Oh, I shouldn't say that, should I? Might offend somebody.
Yeah.
All right.
Somebody wants to know how massive Jupiter is.
How massive it is? Yeah, I don't recall the mass off the top of my head, but its size is 11.2 times the diameter of the Earth. So its volume is what, 10,000, 11 cubed is what, 13,000, something like that?
Its mass is 317.88 Earth masses.
317.88 Earth masses. So thank you, John. He's over there looking it up.
I'm chasing clouds here.
Yeah, we got clouds passing in front of us, so it's going to go dim and bright. And dim and bright. It's
Trying to
actually,
keep up with it. It's like a hand-eye coordination thing.
yeah, we've got a lot more clouds now than we had earlier. So
Yeah,
I think
it's thickening.
probably, yeah, we're probably about ready to wind it up here.
Yeah,
So,
that's probably true. I'm sorry.
so,
It's shrinking.
Yeah, it's shrinking. I'm melting.
amazingly, the temperature has actually gone up since we started. So
Yeah.
So the temperature is now 88 degrees, was 86 degrees when we started. So
All right. Yeah. It's not going to get any better. Now all the high altitude stuff is moving in. Yeah.
yeah.
So it's a slow fade out to the end of our program here.
Yeah.
All right.
So
Well,
a couple of things we should announce.
Yep.
Once again, we want to encourage everybody to donate if they can. Your donations help Chabot Space and Science Center continue to support STEM education, and it keeps us going, keeps the facility going. We are close to the public right now because of the pandemic, but we try to continue to do programming online. And we keep doing that. We're working towards our planned reopening to the public June of next year. So your donations help to support us. You can do that with the donation button on the Facebook page. You can also go to Chabot's website, chabotspace.org, and there will be a donation button up at the top of the page. Click that, and whatever you can contribute. And certainly if you know anybody like your employer or somebody that you know who's got a little extra money to spare, certainly encourage them to donate as well. Also, a couple of upcoming things. This coming Wednesday, Ben Barres, who is the content developer and staff astronomer here at Chabot, he's going to be doing a presentation about the history of Chabot, the early history of Chabot. Chabot has been around for 137 years. And Ben has a really great presentation about how Chabot Observatory got started and its early history.
yeah, it is a really interesting presentation.
That'll be starting at 8 o'clock on Chabot's Facebook page this coming Wednesday. And then next Friday, Chabot is going to be doing a special virtual program on our Facebook page about the 20th anniversary of our move to the current location. We are now up in Redwood Regional Park, up in the Oakland Hills, and we moved here 20 years ago. And so we're going to be doing a special celebration program next Friday, starting at 8 o'clock. And then, of course, you can join us again for Virtual Telescope a week from tonight. Richard and John and I will be at it again.
All
All right.
That's it. Thanks, everybody, for your participation. Good questions tonight. I'll try to answer a few online after we stopped our video presentation. All right. Take care now. Bye-bye.